Warning: glacial acetic acid is corrosive and irritant. Hydrazine is toxic. Sodium dithionite may react violently when exposed in air or mixed with oxidizers. Perform the experiment in a well-ventilated area and wear gloves and a mask when handling them. Hi guys, here is MIH. As a lot of you may know, luminol is a very cool compound because it emits a bright blue light when mixed with a catalyst and an oxidizer like hydrogen peroxide. If other fluorescent dyes are present in the solution, they could emit their distinctive colors as well. The main reason that stops amateur chemists from trying this experiment is the slightly expensive price of luminol, which I thought didn't make sense considering how cheap its precursors are. Its synthesis is also relatively simple among organic compounds. Conventional luminol synthesis routes often start from phthalate esters present in gloves or potassium hydrogen phthalates sold as a pH buffer. However, one of the steps in those synthesis routes will be a nitration, which requires concentrated nitric and sulfuric acids, has a low yield compared to other steps, and is rather dangerous. Therefore, I decided to avoid it and directly bought the nitrated compound, 3-nitrophthalic acid, and it was actually quite cheap from a chemical company. From this compound, the synthesis route is shortened to 2 steps, respectively a hydrazine condensation and nitro group reduction. So first, I prepared the hydrazine condensation reaction. The reaction requires some sodium acetate as the base, so I decided to make some by neutralizing 4.84 grams of glacial acetic acid with a sodium carbonate solution until the pH reaches 9. Then I added in 3 other ingredients: 6.36 grams of 3-nitrophthalic acid, 3.9 grams of hydrogen sulfate, and 24 grams of glycerol as a solvent. The mixture is then placed on a hot plate and heated to 200 degrees Celsius. In my first run, I overshot the temperature and let it rise above 220 degrees and got a bunch of tar. Trust me, it was not fun to clean up even with a concentrated potassium hydroxide solution. In the second run, I carefully ramped it up the temperature until the mixture boils. When most of the water is boiled off, the temperature rises to 120 degrees Celsius, which is the boiling point of acetic acid. The sodium acetate reacts with the hydrogen sulfate to produce sodium sulfate, hydrazine, and acetic acid. The acetic acid boils off, while the hydrazine immediately attacks the carboxylic acid groups on the 3-nitrophthalic acid one by one and kicks off 2 molecules of water, producing 3-nitrophthalate hydrazide. This method of generating hydrazine in situ avoids the usage of dangerous hydrazine hydrate and makes the reaction much safer. When all of the acetic acid boils off, the temperature rises to 200 degrees Celsius and the mixture begins to turn yellow, which indicates that our product is forming. The mixture is maintained at this temperature for 5 minutes, allowed to cool, and poured into 150 ml of cold water. The water will dissolve all of the byproducts such as sodium sulfate, and our product will crash out as a yellow precipitate. The product is filtered off and dried on the funnel. Just confirming if our reaction worked, I added a little bit of potassium hydroxide to the beaker that contained a little of my product, and a bright red color indicates a success. Knowing that the reaction worked, I then proceeded to scale it up and convert all my remaining 3-nitrophthalic acid to the 3-nitrophthalate hydrazide. I have 13.55 grams here, so I again made some sodium acetate using 10.26 grams of glacial acetic acid. I then added in my 3-nitrophthalic acid and 6.97 grams of hydrogen sulfate. I ran the experiment using the exact same procedures as last time, except that I first heated the mixture on a smaller hot plate that could only reach 200 degrees to get rid of the water and the acetic acid, and then switched to my hotter one. I ended up with 14.37 grams of not so dry product, and after combining in my product from the small scale run, I have a total of 19.78 grams of 3-nitrophthalate hydrazide, ready to feed in the nitro reduction reaction. The reduction of nitro groups to amine groups is used quite often, and many different methods had already been developed, so I decided to try something different and deviate from the conventional route. The usual procedure calls for a large excess of sodium dithionite, but I've came across a paper that uses stoichiometric amounts of hydrazine as a reducing agent and iron hydroxide as a catalyst that resulted in higher yields. Just as a side note though, it didn't work. I divided my starting material into 2 equal portions and first processed one portion using the standard sodium dithionite method. I first measured out 25 grams of potassium hydroxide and dissolved it in 100 grams of water. By the way, this is a big excess. The potassium hydroxide solution is then poured into the 3-nitrophthalate hydrazide. The chemical doesn't dissolve well in water, but easily dissolves in alkali to give a dark red solution. I heated the mixture to 65 degrees Celsius, but there are still some insoluble stuff at the bottom. I ignored that and proceeded to measure out 40 grams of sodium dithionite. I bought it as a reducing agent for bleaching textiles, and it came in small 40-gram packages, which I thought was nice because sodium dithionite is very sensitive to air and moisture. I thought it was an excess and I should have some remaining after the reaction, but I completely used it up. I added the sodium dithionite slowly to the alkali solution, and apparently nothing is happening, but after a while the temperature rose to 75 degrees C, which is a good sign as the reaction itself is very exothermic. As I added more sodium dithionite, the mixture gradually turned to a lighter orange-red color and the insoluble stuff disappeared. Eventually, the color stayed as light yellow. The reaction is now complete, but the pH is strongly basic. To get the luminol out, I acidified the mixture using some glacioacetic acid until the pH reaches around 6. Immediately, some yellow-white precipitate appeared, which is luminol crashing out of solution. The two nitrogen atoms on the thiol hydrazide structure of luminol are slightly acidic due to the strongly electron-withdrawing carbonyls nearby. The nitrogen atom on the benzene ring, however, is basic. This gives luminol some amphoteric properties, allowing it to dissolve well in both strong acids and strong bases. Luminol has the smallest solubility in the Zwitter ionic form, where the molecule has no net charge, which is at pH around 4 to 6. After the desired pH is reached, the mixture is filtered. The luminol product appeared as a paste that is difficult to dry, and I thought it was probably not so pure, so I tried to recrystallize it in ethanol. However, as I found out, luminol is nearly insoluble in ethanol, so the ethanol apparently dissolved a bunch of impurities and didn't touch the luminol at all. Well, at least the luminol is a bit cleaner now. Now for the alleged new hydrazine method. I dissolved the other half of the 3-nitrophthyl hydrazide using the same amount of potassium hydroxide. I measured around 1 gram of ferric chloride, dissolved it in water, and added it to the mixture. The paper mentioned an iron hydroxide oxide catalyst prepared from ferric chloride and sodium hydroxide, so I thought directly adding it in the mix also works. I heated the mixture up to 60 degrees Celsius, which is supposed to be the reaction temperature. I then moved outside with the mixture and the stoichiometric amount of hydrogen sulfate I measured beforehand and gradually added it in the mixture. There were no signs of exotherm or color change after 30 minutes. The paper technically called for a reaction time of 4 hours, but I can't heat a dangerous solution containing hydrazine for that long. So I gave up, dumped in 40 grams of sodium dithionite, and did the workup just like before. After a week of drying, I obtained a total of 14.89 grams of luminol product. Now we have to test it to make sure the whole synthesis worked. I just randomly grabbed the recipe from the internet and it needs 2 solutions to work. Solution A calls for 50 ml of water, 0.4 grams of sodium carbonate, and 0.02 grams of luminol. I stirred the mixture until the luminol dissolved. The recipe needs 2.5 grams of sodium bicarbonate, but I only had 1.5 grams on hand, but that'll do. I then added water until the total volume reaches 100 ml. For solution B, I measured out 0.1 grams of potassium ferricyanide, dissolved it in 1.67 ml of 7.5% hydrogen peroxide, and diluted it to 2.5 ml. Here are our 2 solutions, and now for the moment of truth. I mixed the 2 solutions, and apparently it didn't emit a strong blue light as I expected. For a moment I thought the whole thing just failed, but I turned off the light and the solution was indeed glowing. It wasn't exactly the strongest glow, but that is probably because I didn't exactly follow the recipe. But this is more than enough to prove that this lengthy organic project is a huge success. Thanks for watching, and see you soon.